Welcome to qnawire.
So part A of our question has asked us to find the energies of the ground state using the information from the figure. So we have E infinity minus E1, not just the ground state, and the first four excited states. So this would be E2, E3, E4, E5, right? So we know that we're going to say E1 is the ground state. So we know that E infinity minus E1 is equal to HC over lambda 1, where we get lambda 1 from the figure. So this value is equal to 152 nanometers. And we're using the electron volt second version of constant and meters per second version of the speed of light. Those are constants you can look up. Lambda 1, again, 152 nanometers, going to convert that to meters. So that's 152 times 10 to the minus 9 meters. So this gives us a value for E1. We can solve for E1, the negative sign, because at infinity, n equals 0. So E1 is equal to, again, negative, to get rid of the negative sign, 8.1 electron volts. This is going to allow us to get the first four excited states. So we can put in as the first solution. So now we have E5 minus E1 equal to HC over lambda 5, which is 158.3 nanometers. So we can solve E5 here. And we find that E5, so E5 would be equal to HC over lambda 5 plus E1, right? So this would come out to equal, again, E1 is positive, so this is going to be plus a negative. So HC over lambda 5 plus E1 gives us E5 equal to negative 0.326 electron volts. Following the same method for E4, we have E4 minus E1 equals HC over lambda 4. In other words, E4 equals E1 plus HC over lambda 4. And from the figure, we have a value of lambda 4 equal to 162.6 nanometers. This gives us a value of E4 equal to negative 0.5 electron volts. And just following the same method here to find E3 and E2. So E2, E3, we're going to have E1 plus H over lambda 3. Lambda 3 is 170.9 nanometers. So this comes out to equal negative 0.904 electron volts. Keep things looking neat here. There we go. And finally, the last one of part A, we have E2 and equal to E1 plus HC over lambda 2, where lambda 2 is equal to 202.6 nanometers. So this comes out to equal negative 2.034 volts. So these represent our energy in the first four energies of this element. Next, for part B, we're going to find the wavelengths of the first three lines in the short wavelength limit in the Balmer series for this atom. So the Balmer series has a wavelength values of lines that can be found from the formula where E sub n minus E2, right, because it goes from a higher state down to the E2 energy state for the Balmer series, is equal to Hc over lambda n. So we're going to start with n equals 3. So we're going to read this equation to solve for lambda n, the values that we found in part A. So lambda n is going to be equal to Hc by E3C2. In this case, lambda n should be lambda 3. So let's make that so that way we distinguish the different wavelength values. So E3 and E2 are the values we found in part A. Plugging them in, we find that this is equal to 1,000 1 times 10 to the minus 9 meters, or 1,091 nanometers. We're going to write things in nanometers since that's a Q used for wavelengths. Now for n equals 4. Lambda is going to be equal. Same thing as the Balmer series, so to be the n equals 4 to the n equals 2 state, h over sub 4 minus e sub 2. Those values, get a value for lambda 4 equal to 811 nanometers. And then the third one, so the first three are n equals 3 to 2, 4 to 2, and then 5 to 2. So the lambda 5 equation, so it's Hc divided by E sub 5 minus E sub 2. So plugging those values in, we find that this is equal to 724 nanometers. And then last thing we're asked to do is to find the shortest wavelength limit. So the shortest wavelength limit is going to happen when n is equal to infinity. So we'll call this lambda s for lambda short. This is equal to Hc divided by, well, this time we have E infinity, which is equal to 0 minus negative, so this is going to be minus E2. Because it'd be E infinity minus E2, but E infinity is 0. So this comes out to equal 609 meters. Part C says to show that the wavelengths of the first four lines in the short wavelength limit of the Lyman series for the hydrogen atom are all 60% of the wavelength for the Lyman series in one of the electron atoms in a distant galaxy. So the ratio of the shortest wavelength limit in the Lyman series of hydrogen atom, so doing is we're taking the wavelength that we just found here. So we'll call this the hydrogen atom wavelength length lambda s h. So this is just so you can look up. I think that h actually looked like an h there. Divided by the wavelength of s previously there b. So this is equal to 364.7 nanometers. That's the wavelength from the hydrogen atom. Divided by what we just found, 609 nanometers. In these values, and find that this row comes out to equal 0.598. We can box that in as our solution for part B. So therefore, the shortest wavelength is about 60%, because 0.598 is about 60%. Okay, so now based on the observations, explain why this atom could be hydrogen. So this atom could be hydrogen since the spectrum is Doppler shifted by motions away from us. Okay, so we could say, let's be this could be a hydrogen if the spectrum is Doppler shifted away from us at a speed that is a non-negligible fraction of that